Hello, everyone. So I will continue talking about transport calculations in a sub. So as you know, now electronic devices are becoming more smaller and smaller. They are really nanoscale, and at such lengths, it's not possible to use semi-classical transport concepts, and it is needed to take into account quantum effects. Such effects are responsible, for example, for tunneling current that can lead to current leakage in the device, and also quantum confinement effects that when the active layer of the transistor is too thin, for example. And in this case, there are quantized states that obviously affect the properties of the device. And therefore, it is needed to use methods that take into account quantum behavior. And one of the codes that allows to study transport with account of quantum effects is trans-siesta. This is a DFT code using non-equilibrium green function formalism to compute non-equilibrium electronic transport. So siesta performs cell-consistent calculation of Hamiltonian density under open boundary condition with voltage applied, and then TB-trans utility is used to compute transmission and current through non-equilibrium green function formalism. And this method can find application in many fields, as I told, for description of electronic nanodevices, transistors, graphene devices, conductive inks, for nanoscale devices when there are defects or quantum dots, and for such processes as corrosion, where it's important to consider processes with bias applied, and for sensors, and for many other systems. So when we want to see whether we can use trans-siesta for transport calculation, we need to consider length scales. So we know that there is elastic scattering that occurs at static impurities and leads to changes in the momentum, but doesn't affect the coherence of wave function. This kind of scattering is characterized by mean free path. There is also inelastic scattering, which corresponds to interaction with phonons, electron-electron interaction, impurities with internal degree of freedom. They lead not only to change in the momentum, but also introduce random phases, that is the coherence of wave function. And such scattering is characterized by phase relaxation length. And when we are talking about quantum confinement effects, it's important to take into account broad wavelengths. So there are different transport regimes when, depending on how the size of the device compares with this relaxation length. So in classical diffusive transport, we're talking about macroscopic samples with length that is greater than mean free path and phase relaxation lengths. In such case, transport is described by semi-classical Boltzmann equation, and then there is coherent transport in the intermediate regime when there is the length of the device is still greater than mean free path, but smaller than phase relaxation length. There is no decoherence of wave functions, and this corresponds to quantum interference effects. Ballistic transport happens when samples are very small, so that they are smaller than mean free path, and then there are no scattering for electrons. And there is great deviation from Boltzmann equation and breaking of Ohm's law. And in samples with size that is comparable to Broglie length, there is quantization of levels. So we can use trans-siesta in cases of coherence, ballistic transport, and to take into account quantum size effects. Interactions, electron-electron interactions, phonon interactions with phonons. So the case of classical diffusive transport is not described by trans-siesta, but in quantum devices, we really need to describe this kind of coherent transport, ballistic transport, and take into account quantum size effects. So in trans-siesta calculation, we consider this kind of device. So there is a semi-infinite left lead, which is in contact with reservoir for electrons, and right lead, which is also semi-infinite in the right direction, in contact with right reservoir, and scattering region in which two leads are in contact, and there can be some changes in structure, some molecule in the middle between electrodes or whatever. So we assume that electrons incident from the left are in thermal equilibrium with left and right reservoirs. There is complete thermalization of electrons upon entering reservoir, and there is no backscattering at lead reservoir interface. And we use Landau formula for current. So the current is determined by the difference in the integral of the difference in occupations of two into leads multiplied by transmission. And in the limit of small voltages, conductance, low voltage conductance is determined by transmission at Fermi level. So this is what basically Transiesta does this calculation. But what ASAP contributes to is to provide an automated workflow to perform this calculation. So it helps to create the device. It helps to introduce the calculation parameters, to launch the calculation and to control its execution and to analyze the results. So even in ASAP, this workflow is a bit complex because we need a series of calculations, a series of steps. So the first thing that we need to do is to prepare the atomic structures of electrodes and of the molecule or systems that we want to put at the contact of electrons. It's recommended to run a single point calculation for these parts of your system in order to know its properties. Then we build a device for transport calculation using the merge tool and create an electronic transport project. So when we run the electronic transport project, as an output, we get Hamiltonian and density matrix and the voltage applied. And then we use this data in transport post-processing project using TB-trans to compute finally the current voltage characteristic, transmission, and other properties that we are interested in. There is also the possibility of optimizing the device geometry using transport device geometry optimization project.